Good afternoon, everyone, and thank you for attending Liberty Motorsports' first design presentation. My name is Brooks Pierce, and I'm the team captain of Liberty Motorsports. This is our first year at competition, and we are excited to show you the hard work we have put in to make our first electric car. This is a preview of what we will cover during the presentation, and we will start with our vehicle drawings. Our SolidWorks model was created by using a top-down assembly of the vehicle composed of all the mechanical and electrical subsystems. Some of the features that I would like to point out that I will go into more detail later include the triplex rear suspension package, our compact powertrain assembly, and our accumulator or battery case situated below the high voltage shelf. We also have a front view of the car displaying the front suspension assembly, a side view of the car showcasing the rear powertrain system and braking arrangement, and finally, a top view of the car displaying where each component lies along the length of the vehicle. Before we started this design, we developed very comprehensive system goals each team had to design around. The suspension team wanted to emphasize limited vehicle roll and absorb impacts from the road course. The frame and air team wanted to emphasize a strong foundation and structure, so 4130 steel was used as the main construction material. The air team focused on directing airflow over the vehicle and ensuring the smallest possible drag coefficient given the frame structure. The powertrain team set an objective to deliver over 100 horsepower at 80% efficiency, while also designing a compact system that integrated well with the electrical subsystem. The braking system was designed with driver safety and usability in mind, such that the system would be simplistic to use, but also strong enough to withstand the heat and stresses and do some hard, repetitive braking. Based on those system goals, we were able to create a few unique designs that I highlighted earlier in the pictures. Our car boasts a unique rear suspension design consisting of a transverse damper and anti-roll bar that was analyzed with the use of bond graphs. Our braking system uses a custom 3D printed brake component made from carbon fiber infused nylon, and our eccentric tensioners in the powertrain apparatus allow us to tension and adjust the angle of the CV axles simultaneously. Our electrical design features a central compact accumulator, allowing our frame to have a very low center of gravity. Our cooling system and our aerodynamics package is designed to work independently of the low voltage system, preventing heat soak in the motor. These are just a few of the highlights in our vehicle, and with that, I will now hand off the presentation to Amy Washburn, our suspension team lead.
Brooks mentioned earlier, we have implemented innovative designs in our anti-roll bar and transverse damper, while keeping the traditional double wishbone style control arms. The front package consists of the double wishbone system with direct actuation through the Öhlins coilovers. Our main design goal for this year's iteration was to obtain a high level of adjustability among the components, and our 4 TTX25 coilovers allow us tremendous adjustability with damper rates in both compression and extension. Both the front and rear top control arms are shorter in length than the lowers, which allows camber rate to increase negative in bump, keeping the tire contact patch as flat and large as possible. This ideal camber curve for achieving the highest lateral force based on maximum cornering conditions was plotted from tire data from the TTC for various compounds and dimensions. The innovative part of the system comes from the investigation of Koenigsegg's XXX suspension, which introduces a transversely mounted damper connecting the left and right upper control arms in the rear. This traditional additional damper mitigates squat dive behavior as a result of the quick longitudinal load transfer upon acceleration and deacceleration. This idea began as research and then was implemented into the car after the results demonstrated positive effects on the system. A reduction in amplitude ratio of both the left and right wheels, and reduced sensitivity of wheel disturbance on one side to the other, while not interfering with sustained displacements such as desired cornering effects. Lastly, as you can see in the lower picture, we added an anti-roll bar to our rear suspension. We did this because without the anti-roll bar, the car saw about 1.5 degrees of body roll in max conditions. The anti-roll bar was thus designed through geometry and material selection to absorb the extra 0.5 degree to stay within the desired limit of the car of 1 degree. Now I'm going to hand it to Mike Gentry to show you our frame.
A key part of the design is the raised front bulkhead. The goal is to allow the driver to sit lower and result in a more aerodynamic car. The rest of the design revolved around keeping the vehicle simple. As this is our first vehicle, we assumed there would be many unseen challenges, so creating a functional car within the rules is our main priority. Having a competition car will serve as a base model to improve on for future Liberty Motorsports teams. The frame is modeled in SolidWorks. It is constructed entirely out of ASI 4130 steel tubes because of their strength and our ability to weld the material. The notches were laser cut and welded into a single solid structure. The frame was then powder coated to increase durability. To verify the frame strength, simulations were done to demonstrate the frame would not fail in collisions, specifically in head-on collisions at 30 miles per hour. Future refinement could include utilizing lighter materials such as carbon fiber or aluminum and shortening our cockpit as it is longer than required, and this would reduce weight. We also learned that the frame design should begin around the suspension to avoid future problems. Now, I'll hand it over to our aerodynamics lead engineer, Aaron Young.
The vehicle's body package is comprised of 3003 aluminum sheet metal and a custom-made carbon fiber nose cone that features an inner layer of fiberglass to avoid any direct contact with the aluminum sheet. Our cooling system is a closed pressurized loop with a regulator cap and an overflow reservoir to ensure static temperature and pressure in the motor and MCU. The bodywork design is more of a focus on basic functionality rather than aerodynamic efficiency. We wanted for the first vehicle we made to ensure that all critical components of the driver were covered and safe, and that we were rule compliant. As this is the first design, an initial CFD simulation was conducted to determine baseline data for the overall drag coefficient of the vehicle. Our cooling system was based upon an assumed motor and an MCU efficiency of around 92%. And we took into consideration the stated burst pressure for each of these components. After testing, we hope to have an accurate temperature data set to be used as a basis for further optimization. Now I'll toss it over to Sam Scott, who's going to talk about our powertrain.
Hi, my name is Sam Scott. I'm the mechanical team lead for our powertrain subsystem. We worked with our electrical counterparts to create the design that you see before you today. As a first-year team, we really had two main decisions that we made in designing this. First, we wanted to minimize our mass and rotational inertia as much as possible, and of course, we wanted to create a simple but robust system with few moving parts. To this end, we created this system, which is a rear-wheel single-motor chain drive. This has really allowed us to break into the world of formula and learn more about classic vehicle dynamics before looking forward to more complex multi-motor setups in future years. Our motor is the MRAX 228. It's capable of putting out 230 newton meters of peak torque all the way up to 3,000 RPM. Using this and a couple of other parameters such as final vehicle mass and drag coefficient, we were able to calculate an optimized gear ratio of 3.615 to 1. This gives us a 0 to 60 time of 5.4 seconds and a top speed of 82.7 miles per hour on paper. In addition, since our vehicle has a slightly longer than average wheelbase, we chose to use a Drexler clutch-based limited slip differential. In terms of manufacturing, we wanted to stray away from custom-made parts as much as possible. However, we did custom manufacture our drive sprocket, our motor mount, our scatter shielding, and our chain tensioners. Finally, although our construction is done, our job is not complete. We are still using test data actively to make sure that we optimize performance both in our motor's control tune and our differentials tune parameters.
Thank you, Sam. So as a first-year team, our main objective in the electrical subsystem is to overcome expected and unexpected difficulties to be able to manufacture a safe and functional electric race car that will compete well in competition. To the right of this slide, you see a simple block diagram describing our electrical system. The low voltage connections are shown using blue wires of gauges ranging from 28 gauge to 12 gauge, and the high voltage is shown using red wires of all highly insulated 4-aught cable. To the left are our main control units, and I will now hand it off to Curtis to elaborate further.
Alrighty, thank you, Colby. So we have 3 control units in our car, all of which are communicating to each other through CAN. Our first and main control unit is the ECU, or the electronic control unit. It is from New Eagle, and it has 28 inputs and 26 outputs with a logic high of 5 volts. We also have a controller for our motor. It is the M-Drive 500. It has a 95 kilowatt hour peak output, and also our accumulator management system, the Orion BMS2, reads up to 48 battery cell voltages and temperatures. And we also have a 4.48 kilowatt hour accumulator with a 40 amp hour capacity and a nominal voltage of 115 volts.
Thank you, Curtis. So, as we near the completion of the electrical system, we are on track to successfully accomplish our main goal of manufacturing a safe and functional car. I'll now hand it off to Mike to discuss the cockpit.
Most of the design for the cockpit components were driven by Formula FSAE rules. The size of the cockpit, dimensions of the head restraint plate, and seatbelt selection were determined based on these requirements. The head restraint was designed to be strong and have lateral adjustment. The dashboard was designed around the existing frame and electrical component needs, and the seat was designed to provide comfort to the driver. The steering is a mechanical rack and pinion design, and the steering column cover was designed to fit within the internal cockpit clearance and cover moving parts near the driver. The head restraint was built from steel plate, angle irons, and steel rods welded to the frame. Flat steel pieces attached to the plate and the angle irons diagonally to provide additional lateral support as it's adjusted. The seat is constructed of an aluminum shell, expanding foam, and rubber coating. The dashboard is water jet steel, and the steering column cover consists of steel plates welded together with smooth edges. The head restraint and seatbelt mounts were analyzed via hand calculations and simulations to ensure they meet the safety requirements. Now I'll hand it over to our brakes lead engineer, Daniel Sheik.
Our design goals are to design a simple braking system that can withstand heavy starts and stops, minimize cost of material and their complexity, and we want our rotors to be able to withstand the high temperatures that will occur during the dynamic events. The material we're using for the pedals and the pedal box plate is 6061 aluminum. This is because it's strong enough to withstand the 2000 Newton force requirement for the pedals, while it's also lighter than steel. When it comes to our rotor assembly, we purchased Wilwood PS1 calipers, which are performance calipers made for small-scale vehicles. We also designed and manufacture our own rotors in-house out of cast iron. This is because cast iron has been simulated to be strong enough to prevent fractures, while also being able to withstand the high amounts of heat that will be observed during the endurance portion of the competition. The simulations performed on the rotors were assuming a maximum temperature of 750 degrees Fahrenheit, and it was found to have a maximum deformation of 0.7 thousandths of a meter, which is very small. Because safety of the driver is of utmost importance, if there were to be a failure in the braking system, our brake over travel switch has been tested and confirmed to shut down the motor. And with that being said, I'll now hand it off to Daniel Bolig, our technical director.
We have arrived at the design you have just seen through 3 years of research, design, analysis, and testing. This process began with the goals shown on this slide. First, we designed our vehicle to reliably complete every static and dynamic event during the competition. Our first goal was to make the vehicle fully rules compliant so that it could get through each step of the competition, beginning with step 1. We accomplished this by requiring every team member to be intimately familiar with the rules. Also, our technical director and our documents manager made regular checks for rules compliance during the design. We also focused on reliability. For instance, we chose to overbuild components that tended to be a point of weakness, such as the control arms. Our second design goal was to make manufacturing and repair simple. For one example, we chose to use very few composite parts. We made most of our body panels out of aluminum, which reduced manufacturing cost and complexity. For another, we kept electrical repair simple by centralizing components in only 2 locations, just above the accumulator and just below the seat. These system design goals together helped us create a reliable, safe, and simple vehicle. Next, I introduce Jacob Walker, the lead for our simulation and analysis team.
Data is extremely important to our team. We use data to ensure safety in real time, validate our design, tune our vehicle, and educate future designs. Our data logger, the AIM Evo 5, is configured to collect data from linear potentiometers and speed sensors at each wheel, 4 strain gauges on the anti-roll bar, GPS, and gyro and accelerometers. The system also connects to the ECU using CAN, allowing us to read and record temperature data, pedal positions, motor RPM, and any other data the ECU collects. Utilizing the built-in Wi-Fi, we're able to monitor the condition of critical components in real time to ensure driver and vehicle safety. The included software allows us to easily analyze our data so we can tune our vehicle according to test data, as well as compare vehicle configurations and lap times. We'll also be able to use the data we collect from this first vehicle to inform future designs and show quantifiable improvements each year. Now I'm going to pass it on to Brooks for the conclusion.
Thank you, Jacob. So after competition and presentations, we will analyze feedback from the judges and debrief all members to analyze what can be improved and how to eliminate the obstacles we faced during competition. This data and feedback will be used to continually improve the team and future vehicle designs. We want to identify weak areas and work to strengthen them before the next competition season. This concludes Liberty Motorsports design presentation, and we look forward to talking with you in the breakout rooms. Thank you so much.